Hi guys, and welcome back to Three Inquisitive Kids. If you don't know yet, my name is Karen, one of the recorders on this channel. And on the Inquisitive Kids YouTube channel, our goal is to help you advance your levels in mathematics wherever you are, and to also help you develop a curiosity of mathematics to learn more and a love of it, and just basically the willingness to explore more when you have a problem and enjoy and appreciate the beauty of mathematics. So in this lesson, we will be starting our unit on functions, which is unit 4 of 8th grade math. So in this lesson, we're going to be learning about the definition of functions and their properties. In this unit, there will be 4 main lessons, but as you can see, the last 2 lessons are split up into multiple parts. So there's actually going to be a total of, let's see, seven videos in this unit in 4 lessons. So here is our first lesson, Introduction to Functions. Learning goals. Understand the concept of functions and the representation methods of functions, and evaluate the value of functions and determine the value range of independent variables. The world is constantly changing, ranging from celestial bodies in the sky to the smallest molecules. Everything is in constant motion and change. So how can we describe these changes and find patterns from a mathematical point of view? So this is where functions come in. The methods of expressing functions. Let's look at scenario 1. I'm sure most of us have ridden a Ferris wheel before. And if you haven't, it's basically this big wheel that you can see in a lot of amusement parks, and there's little cars with seats in them attached to this wheel. And what it does is basically it rotates, and it's just very relaxing to slowly cruise up the wheel and then down. So the question is, when you're riding a Ferris wheel, how does your height relative to the ground change over time? Well, let's look at this on a graph. Here on the x-axis is t, which represents minutes, and the y-axis is h, which represents the height in meters above the ground. As you can see right now, we have a Ferris wheel. So when you're just starting to get onto that Ferris wheel, that starting point, you're at 3 meters above the ground. 3 meters above the ground. A little while up, you are at 10 meters above the ground. And then you're at 37 meters. 45. And then now, as you can see, you are starting to come down. So when you're starting to come down, the dotted line we have to describe this is green. And you're at 37. Here you are still at 10 meters, and then finally you go back to where you started, which is 3 meters above the ground. So altogether, this forms this curve pattern, right? Because you go up and down, up and down. And this makes sense because it's a circle, so it's not a straight line up. It does take some time for you to get a natural wave to get you from down here to the very top. So this is how you express the function of a car's height on a Ferris wheel relative to the ground over time, and describing it on the graph. In this graph. So the figure below reflects the relationship between the height h in meters of a point on the Ferris wheel and the time, which is t, meaning minutes. So if you were to fill in a table based on this graph, what would it look like? Well, your starting point would be 3. So you would write 3, 10, 37, 45, and then you start coming down, so 37 and 11. And for a given time t, can the corresponding height h be determined? So now that we have this relationship, if I give you a random value for t, so a random length of time, can you, using this pattern that we've just found, can you give me a corresponding height? So that's the question right there. Think about this for a moment. On this table, if I gave you any value for t, could you give me a corresponding height to h? Scenario 2. Cylinders are stacked as shown below. How does the total number of objects change as the number of layers increase? Well, let's fill in the table. We have a table right here, and the top is the number of layers, and the bottom is the total number of cylinders. So if there is only one layer, there is one cylinder. 2 layers, 3 cylinders. 3 layers, 6 cylinders, and it keeps going on like this. So what's the pattern here? For a given number of layers n, can the corresponding total number of objects y be determined? And how many y values does each x value correspond to? What this is asking is, if I give you any value for n, can you give me a value of y that corresponds to it? And is there only one value that can correspond to it as its y, or can there be multiple? So the answer is there is only one y to every x value. For every input value, there is one output value. So let's look at our final scenario. The volume of a certain mass of gas remains constant. If the temperature drops to negative 273 degrees Celsius, the pressure of the gas is 0. Therefore, physics regards negative 273 degrees Celsius as the 0 degree of thermodynamic temperature. Thermodynamic temperature, which is T, represented by T, and Celsius temperature, in lowercase t, which means, in degrees Celsius, have the following relationship. Thermodynamic temperature is equal to the Celsius temperature plus 273 when the uppercase T is greater or equal to 0. So when T is equal to negative 43, negative 27, 0, and 18 respectively, what is the corresponding thermodynamic temperature T? So when T is equal to negative 43, the thermodynamic temperature would be 230. And so these respectively would be 230, 246, 273, and 291. Number 2. Given any value of the Celsius temperature T greater than negative 273 degrees Celsius, can the corresponding thermodynamic temperature T be determined? How many T values are there corresponding to it? So again, as long as this Celsius temperature is greater than negative 273 degrees Celsius, can I give you any value of the lowercase t, and then based off of a pattern, you give me a corresponding uppercase T representing its thermodynamic temperature. There is a one-to-one correspondence between a Celsius temperature and its equivalent in thermodynamic temperature. So here's our conclusion. What similarities do all of the previous questions share? Well, there's always two variables. In the first one, there was the time, which is t, and its corresponding height, which is h. In the second scenario, there was the number of layers, n, and its corresponding total, which is y. In the last scenario is the Celsius temperature T and its corresponding thermodynamic temperature uppercase T. So here are their similarities. There are two variables in each scenario, and if we are given the value of one of the variables, the value of the other variable can be determined accordingly. Conclusion. Usually if there are two variables, x and y, in a process of change, And for each value of variable x, variable y has a unique value, so one-to-one correspondence to it, then we say that y is a function of x, where x is the independent variable. So two very important vocabulary words just came up. Function of x and independent variable. What does independent variable mean? Independent variable means that from the problem, this is a variable that changes on its own. For example, here is what I mean. X is equal to 2y, for example. Or 2y is equal to x. Never mind. So 2x is equal to y. Here, x is the independent variable because it changes by itself. Y is the dependent variable because it is based off of whatever x is. It depends on x. So that's kind of the gist of what independent variable and dependent variable mean. Notice, a function is not a number, but instead refers to the relationship between two variables in a certain change process. So the general methods to express functions are the graphing method, which is what we looked at with the Ferris wheel, the table method, we used tables a lot, and also the relational method, or otherwise called the analytic method or the expression method. So scenario 1, we used the graphing method when we graph the height of a point on the Ferris wheel on a graph. The second one, which was with the cylinders, we used the table method so we can find the pattern. And for the third one, yes, we also did use a table, but we mostly looked at that expression, that relationship that was given in the problem. So these three ways are all methods to express functions. Discuss. The graph of y and x is graphed as shown. Is y a function of xa? So here, for example, if x has a value of 1, its y value is both 2 and negative 2. So this would not be a function because, remember, a function has to between x and y, one input has to have one output only. But here, one input, x, has two outputs, y. So this is not a function. In the following figures, if x is the independent variable, would y be a function of x, y or y not? Again, this would be a function because for every x value, there is only one y value. Remember, we didn't say for every y value, there's only one x value. We only said for every x value, there is one y value. Okay, those two things are different. Don't be confused. But for this next one, it is not a function. Y is not a function of x because for every x value, there are two y values. And so that means it cannot be a function. So here y is not a function of x, and here y is a function of x. Example 1. Among the following relationships between x and y, so there are 5 different relationships between x and y shown. So the first one is y is equal to 2x plus 3. Second one, y is equal to x squared plus 3. The third one is y is equal to 2 times the absolute value of x. Fourth one, y is equal to positive or minus square root of x. And the last one is y squared minus 3x is equal to 10. So which ones show y as a function of x? Well, let's look at both of them. Y is a function of x in scenario 1, 2, and 3, because in all of these scenarios, a x value has two y values. Have one x value and one y value that corresponds to an x value. Method conclusion. The key to determining whether a variable is a function of another variable is to see that when one variable is determined, the other variable has a uniquely or one-to-one correspondence determined value corresponding to it. Alright, now we're going to look at the value ranges of independent variables. In the previous 3 questions, what values can the independent variables take to make the function meaningful? So again, let's look at our Ferris wheel scenario. Here is our graph. What is the value range of the independent variable t? Well, that would be when t is greater or equal to 0. Because it doesn't make sense if t is less than 0. If t was -1, for example, does it make sense that you were on the Ferris wheel for -1 minutes? No, because in real life that does not exist. So in order to make the function meaningful or to make it make sense, in this scenario, t will have to be greater or equal to 0. Now let's look at our second scenario. Cylinders are stacked as shown below. How does the total number of objects change as the number of layers increase? So again, we have our table here. What is the value range of n? Well, it doesn't make sense to have -7 layers of n because you can't have a negative amount of layers. That wouldn't make sense. So n would just have to be a counting number. Okay? N is a counting number. So a counting number, remember, is a positive integer. So 1, 2, 3, 4. 0 and all negative numbers are not a counting number, neither are decimals nor fractions. Scenario 3. The volume of a certain mass of gas remains constant, so this is the exact same problem. So what is the value range of t? Well, here it is given that so the lowercase t has to be greater or equal to -273, since the uppercase t, or thermodynamic temperature, has to be greater or equal to 0. Let's do a problem. There is 50 liters of gasoline in the fuel tank of a car. If there is no more refueling, the fuel volume, Y unit liters, in the fuel tank will decrease with the increase of the mileage, X unit kilometers, and the average fuel consumption would be 0.1 liters per kilometer. Express the functional relationship between Y and X. So here it's asking us to write an equation that shows the relationship between X and Y. And that would be Y is equal to 50 minus 0.1 X, because we start with 50 liters, but with every kilometer, we subtract 0.1 liter. So that would be 50 minus 0.1 X. And what does 0.1 X represent? Well, that is an amount that is used. So here is the relational expression we can write, or functional relationship. So the relational expression we can write to describe this function. Number 2, find the value range of the independent variable of x. So what range of values can x take to make this function seem appropriate, to make sense? Well, because x is greater than or equal to 0, and 50 minus 0.1 x has to be greater or equal to 0, the mileage of the car and the amount of fuel in the fuel tank cannot be negative, because that just does not make sense. So the value range of x is greater or equal to 0 and less than or equal to 500. So this is the value range of x. When determining the value range of the independent variable, not only should the analytical expression or relational expression of the function be considered meaningful, but you also have to think about the actual meaning. Okay? Because here, if we just look at that relational expression, we would only get x is greater or equal to 0. But if you look at the problem, you also have to add this less than or equal to 500. So this would be the value range of x. How much fuel would be left in the tank when the car has driven 200 kilometers? When x is equal to 200 and the value of the function y is equal to 30, therefore, when the car travels 200 kilometers, there will be 30 liters of oil left in the tank. Exercise. What is the value range of x in the following equations? Pause the video and solve this on your own. Alright, so for the first one, you should get x is any real number. X can take any value and it would still be an okay expression. X plus 2 cannot equal 0 because you cannot have, in mathematics, you cannot have a 0 on the denominator of a fraction. So x cannot be equal to -2. Number 3. So here, it does not make sense for x minus 5 to be negative, so it has to be greater or equal to than 0, meaning x has to be greater or equal to than 5. Y is equal to the cube root of 2x plus 1. X can take any real number. And for the last one, y is equal to the square root of x plus 2 divided by the sum of x and 1. Well, there's two things you have to think about now. X plus 1 cannot equal 0, and x plus 2 has to be greater or equal to than 0. Therefore, x cannot equal -1, and x has to be greater or equal to than -2. So here, this would be on the number line how we're going to express this inequality. And this open spot on -1 shows that it's all of these values except for -1. So x is greater or equal to -2, and x cannot equal -1. Now we're going to talk about the values of functions. Scenario 3, the functional relationship between the uppercase and lowercase t's is the thermodynamic temperature is equal to the temperature in Celsius plus 273, where, so in parentheses, you also have to write the value range of the thermodynamic temperature or the independent variable. So that would be T is greater or equal to than 0. So when T is equal to 1, the thermodynamic temperature would be 1 plus 273, or 274. Then 274 would be the value of the function when T is equal to 1. Basically, you can think of the value of a function as for a definite value of the independent variable within the range of possible values, the function has a unique corresponding value, which is called the function value, when the independent variable is equal to a, representing a number. So if y is a function of x and x is equal to a, y is equal to b, then b would be the function value when x is equal to a. So you can think of a value of a function as the result you get after substituting in a value for the independent variable. That would be the output of that function. Input, output, that would be the output. So reminder, a function is not a number, but instead refers to the relationship between two variables in a certain change process. The function value is a number, which is the value of the dependent variable when the independent variable is determined. So we talked about how these two variables, the independent and the dependent variables, have a one-to-one correspondence in functions. So a function value would be the corresponding value of the dependent variable when the independent variable is given. Let's do this problem together. In the function y is equal to 4x minus 2 divided by x plus 1, let's first find the function value when x is equal to 2, equal to 3, or equal to -3. The value of the function can be obtained by substituting these values into this function to get that output. So we're substituting, and then we have 2, 5 halves, and 7. Question 2, what value must x be in order for the function value to be 0? So now you're given the function value is 0, and you want to see what input value satisfies that. So you could first substitute 0 as y, as the output value, and then solve for x. So then solved, x would be equal to 1/2. Therefore, when x is equal to 1/2, y is equal to 0. Class summary. Today we learned all about functions, its definition, the 3 methods of expressing functions, the value range of independent variables, and function values. The two skills we learned today is to understand the concept of functions and its representation method, as well as to evaluate the value of functions and determine the value range of independent variables. So these are the two important skills that we learned today. And functions is a very important topic that we are going to be building off of as we go into this unit. So this lesson is very important foundationally for the rest of this unit, as well as just the rest of your mathematical career. So this is very important. If you didn't get something, you can either ask us in the comments down below, or you could just always go back in the video, rewind, and then watch it again. So if you liked this content, if it helped you, if you learned something new, please feel free to click that like button down below. And if you would like to be notified the next time we upload videos, you can also click that notification bell as well as the subscribe button, so you will be notified. Thank you so much for watching Through Inquisitive Kids. We really appreciate it, and we'll see you next time.